This is a classic problem involving the wave functions of a particle trapped in a simple harmonic oscillator system. And this is a problem taken from David Griffith's Introduction to Quantum Mechanics, second edition. And this problem can be solved in two different ways. One, you could use the concept of Hermite polynomials. One, use Hermite polynomials. And two, you could also use the concept of the ladder operators. Now, what if you do not have access to the Hermite polynomials, because these are sets of polynomials that extends from n equals 0 to n tends to infinity? You would definitely have to use the concept of ladder operators if you'd like to solve these problems. Okay, so let's begin with ladder operators. And the ladder operator case is what we are going to use to solve this problem, not the Hermite polynomials. Okay, so the first question says, construct psi of 2. All right, so we have to construct psi of 2 in the simple harmonic oscillator. And recall that since we are using the concept of ladder operators, any psi of n, any psi of n can be written down as 1 over the square root of n factorial times a plus to the power n times psi of 0, where a plus was negative I plus m omega x all over the square root of 2h bar m omega. And this is very important to recall that your p, which is this, and your x, both are operators. Well, x operator is basically x, but p, your p operator, is basically negative h bar, the first derivative with respect to x. All right, so let's construct psi of 2 then. In order to construct psi of 2, according to this formula over here, psi of 2 would be 1 over the square root of 2 factorial times a plus raised to the power 2 times psi of 0. We know what our psi of 0 is, which is the ground state wave function, and this is m omega all over pi h bar raised to the power 1/4 times e to the negative m omega x squared all over 2h bar. Okay, so let's do a plus on psi of 0, and then when we have a plus on psi of 0, we will proceed to do a plus on a plus psi of 0, which is basically a plus squared times psi of 0 on psi of 0. This is our second step, but our first step would be to do a plus on psi of 0. Okay, so a plus on psi of 0 would basically be 1 over the square root of 2h bar m omega times negative I p plus m omega x times psi of 0, which is m omega all over pi h bar to the 1/4 times e to the m omega x squared all over 2h bar. Okay, so let's detail out the operator p over here, and we get that this is basically equal to this times m omega all over pi h bar raised to the 1/4. I'm pulling this out of here, and inside you get negative I times negative I ddx, which is basically your p operator plus m omega x to the times e to the m omega x squared all over 2h bar. I should make this clearer. All right, so what you basically get is m omega all over pi h bar raised to the 1/4 times 1 over the square root of 2h bar m omega. All right, and over here, oh, I forgot, this should also have an IH bar over here. My bad. So adding the IH bar over here gets us to negative h ddx of this function over here plus m omega x times e to the negative m omega x squared 2h bar. Okay, so next step would be to take the first derivative of this function over here. Okay, so if you take the first derivative of the function outside, then you're basically left with the following: negative h bar times the first derivative of that function inside, which is basically negative m omega x squared all over 2h bar times the derivative of x squared, which is 2x times e to the negative m omega x squared all over 2h bar plus m omega x e to the negative m omega x squared all over 2h bar. Okay, we can further simplify the things that we've written so far, and we get the following. The constants remain the same. This entire thing over here can be simplified into m omega x. Oops, I just realized I wrote down an x squared over here. There shouldn't be an x squared. Yeah, this entire thing can be simplified into m omega x plus m omega x over here from this term, and outside we can bring out our exponential, right? So this entire thing just becomes 2m omega. Let me write this down in this way. This is equal to 2m omega x All right, so our final term just becomes 1 over the square root of 2 h bar m omega times m omega all over pi h bar raised to the 1/4 times 2 m omega x e to the negative m omega x squared all over 2h bar. All right, so this is basically your a plus acting on psi of 0. Let's do a plus squared acting on psi of 0, which is our second step that we discussed over here, which is this. All right, so now that we have our a plus psi of 0, let's do a plus squared psi of 0. Let me use a different ink. So a plus squared on psi of 0 is basically a plus acting on a plus psi 0, right? And a plus acting on psi of 0 is basically the same thing that we is similar to what we did previously. We're going to write down our step up or raising ladder operator, which is this, and this is basically going to act on our a plus psi of 0, which is basically this. All right, so by expanding everything out, and I'll leave this entire thing up to you, you would have that this is basically m omega all over pi h bar 1/4 times 1 h bar, no, times negative h bar ddx of x e to the negative m omega x squared all over 2h bar plus m omega x squared e to the negative m omega x squared all over 2h bar. I expanded everything out. This is just tedious algebra, but I'm pretty sure you'll be able to do this. Okay, so we have to take the first derivative. We have to take the first derivative over here, right? So taking this entire derivative, let me use a different ink. This is basically equal to taking the chain rule, doing the chain rule, right? So this basically equals to x times negative m omega all over 2h bar times 2x e to the negative m omega x squared all over 2h bar. 2h bar plus e to the negative m omega x squared all over 2h bar. This is what it looks like when you take the first derivative. Okay, so plug it back into this equation over here, and you have that this is basically m omega all over pi h bar raised to the 1/4 times 1 over h bar times x times negative m omega 2h bar times 2x times negative h plus, minus h bar plus m omega x squared times e to the negative m omega x squared all over 2h bar. Okay, you can further simplify this entire thing. For example, the h bar and h bars, they cancel out, they divide out, and the 2's divide out over here, right? So you have m omega all over pi h bar raised to the 1/4 times 1h bar times negative m omega x squared minus h bar. This actually should be a positive because this h bar should have a negative sign right next to it. Okay, so m omega x squared minus h bar plus m omega x squared e to the negative m omega x squared all over 2h bar. So see this, you can combine these two terms and this just becomes 2m omega x squared minus h bar. Okay, minus h bar, and I can of course bring this to the left. Okay, now see, I also have an h bar in the denominator over here, so I can bring this inside the expression over here, right? So if I do that, I get something that looks like this. Okay, and this basically equals 2m omega x squared all over h bar minus 1, right? So finally, we have that our a plus squared on psi of 0 is basically m omega all over pi h bar raised to the 1/4 times 2m omega x squared minus 1, but the first expression has an h bar in the denominator, times e to the negative m omega x squared all over 2h bar. But our final expression for psi 2 is basically 1 over the square root of 2 factorial times a plus squared psi of 0. Okay, so psi 2 basically becomes 1 over the square root of 2 times m omega all over pi h bar raised to the 1/4 times 2m omega x squared all over h bar minus 1 e to the negative m omega x squared all over 2h bar. And this is basically your answer for psi 2. Part A done. All right, so let's look at what the question says for part 2. Part B or part 2 says sketch psi 0, psi 1, and psi 2. So this can be either done using Mathematica or any graphing tool that you would have, and there's also an intuitive way of drawing or sketching these two functions. Let's begin by writing down what the wave functions actually look like for each of those cases. Psi of 0 is m omega all over pi h bar times 1/4 e to the negative m omega x squared all over 2h bar. Well, psi 1 is m omega all over pi h bar raised to the 1/4 times 2m omega all over the square root of 2h bar m omega times x e to the negative m omega x squared all over 2h bar. We'll get to psi 2, but let's do psi 0 and psi 1 first. See, notice this entire expression over here. We have an exponential that has the form of e to the negative bx squared, where b is any constant, multiplied by some arbitrary constant a. All right. Notice that this function, the exponential function e to the negative bx squared, is an even function times just a constant. So this entire function over here is basically an even function. This is an even function, right? So when you plot or sketch your even function, x in the x-axis and in the y we have psi of 0, this has the approximate figure that kind of looks like this. All right, so this is your psi of 0, and this is an even function. Similarly, for psi of 1, this kind of has the format of some constant a times x times e to the negative b x squared, right? Notice that x is an odd function, and e to the negative bx squared, as we discussed, was an even function. So when you multiply these two things, an odd function and an even function, your result would have the form of an odd function, right? So when you basically plot it or sketch it, x in the x-axis and psi of 1 in the y-axis, this kind of looks like the following. And your final product is basically an odd function. I'll leave you to find out how psi of 2 looks like and why the reasoning behind it is. Well, psi of 2 basically is this when you write down the wave function, 2m omega x squared all over h bar minus 1 e to the negative m omega x squared all over 2h bar. Okay, but your final sketch can either be found out using Mathematica, or you could use the concept of even and odd functions as well. I'm going to sketch it for you. It should kind of look like this. Okay, so this is psi of 2, and this is x. As you can clearly see that this is an even function. All right, let's look at question C. So question C basically tells you to check the orthogonality of the wave functions by explicit integration. And for the hint, it says if you exploit the evenness and oddness of the functions, there's really only one integral left to do. Okay, let's test it out. So for C, let's first explicitly write down the wave functions, psi of 0, psi of 1, and psi of 2. And for part B, we already have them, so I'm just going to copy paste them. So we have our wave functions over here. We know that psi of 0 is even, psi of 1 is odd, and psi of 2 is even. All right, so if this is the case, then if you do psi of 0 and psi of 1, their orthogonality test, which is basically taking psi of 0 conjugate times psi 1 dx, you're basically going to get 0 because these are even and odd functions. This is an even function, this is an odd function. Same goes for the integral of psi of 1 star times psi of 2 dx. You're dealing with an odd function and an even function. So when you multiply them, you basically get an odd function. And the integral of an odd function is basically 0. So what's only left to test out is the integral of psi 0 star times psi 2, which is psi 0 star times psi 2 dx. So let's test that out. So first of all, we are going to write down our wave functions over here. And that's basically equal to m omega pi h bar times 1/2. I multiply these two and you get 1/2 times 1 over the square root of 2, which is this term over here. I should indicate to this one. Okay, so 1 over square root of 2 times the integral of 2m omega all over h bar x squared minus 1 times e to the negative m omega x squared, but h over here, because when you multiply these two terms, it becomes an h in the denominator, times dx, and the bounds should be from negative infinity to infinity. Okay, so let's solve this integral over here. Now, for convenience, we are going to treat this as some constant a, and if we write down the entire thing, we have some constant a times this entire integral over here, and we can split this integral into two parts. One is 2m omega all over h bar times the integral of x squared e to the negative m omega x squared all over h bar, minus we have just the integral m omega x squared all over h bar dx. All right, so see, this integral, let's call this I2. I2 is basically your standard Gaussian integral, right? E to the negative a x squared dx, where a is some constant. A, in this case, is m omega all over h bar. And this results the square root of pi all over a. Now, as for this one, this has the form of I1 being equal to negative infinity to infinity of x squared e to the negative a x squared dx, where of course a is this. Now the answer to this integral is 1 over 2 pi times pi all over a cube and its square root. And of course you can simplify this and write it down like this. All right, this is I1. All right, and this can be solved, this entire integral can be solved using the Feynman technique, a video tutorial that I plan to upload soon. But for now, let's take this answer as for granted. So our final product just becomes some constant a times 2m omega over h bar. So this is basically 2a if we associate a into it. So this is basically 2 times a times I1. I1 is 1 over 2a times the square root of pi all over a minus this, the square root of pi all over a. So 2a, they divide out, and you're left with just 0. All right? So what this is basically saying is that the integral of psi 0 star times psi 2 dx from negative infinity to infinity is 0, which means what? Psi 0 and psi 2 are orthogonal to each other, which is consistent with the orthogonality test that we did previously on our stationary states. The stationary states are orthogonal to each other, and it's reconfirmed using this integral. Remember the orthogonality test where it said that negative infinity to infinity, the integral of psi n star psi m dx gives you the conical delta? And the conical delta basically tells you that it's 0 at every place where n is not equal to m, but only 1 when n is equal to m. Well, that's basically it then. That's all.